The concept actually is very simple. The concept is actually very simple. So we start with 1D elements. This is 條狀嘅構件. So what are one-dimensional elements? Those are things that you are familiar with: beams, columns, cables, something called tie, T-I-E, tie, and piles. Those are common elements, one-dimensional elements in a structure. So what is so special about these things? These things usually are very long, right? Very long, and the cross-section is relatively small. So you can draw it like this. So assuming that the cross-section is rectangular, that's the length. Alright? So if I call the length L, this is a rectangular cross-section. So I can call the cross-section, this is lead to A, this is lead to B. So if you compare the cross-section with the length for a beam, a column, a cable, a tie, or a pile, usually the cross-section is much smaller. So in other words, you can write it down, A and B are usually much smaller than L. Example, for a beam, a typical beam in a building, or let's say a residential building, a typical beam size. It could be, let's say, 300 millimeter for A, sorry, for B. And then this lead to A, the depth, let's say 600. And then what about the length? 5 meters, 6 meters. So L could be, let's say, 6 meters. So you can see it's at least 10 times. 10 times. Okay, so that's what we mean by a one-dimensional element. For, let's say, for a pile, what about a pile? Let's say a ball pile. Let's say a ball pile. The smallest one could be 1 meters in diameter up to 2.5. All right, so let's say, for example, 2 meters diameter. What about the length of the ball pile? It could be 30 meters, 50 meters, 80 meters. Let's say 50 meters long. Right, so just to give you an idea, the difference in size, I mean the dimension of the cross-section against the length, it's a big difference. Right? At least 10 times. But you need also to pay attention that the one-dimensional elements doesn't have to be a straight member. It could be a curved member. So it's okay to have a curved beam. Right? So I can draw a curved beam like this. Right? So in that case, it's still, the assumption here is still true for this case. Only the exception is this L is not a straight line, it's a curve. But it's still very much longer or much larger than A and B. So it can be straight, it can be curved. And then if you extend the concept to a two-dimensional element, Same thing. What is two-dimensional element? So I'll give you some hints. Slabs, walls, something you learn in your year one, raft footing or raft foundation. So what is a typical, let me just draw a slab or wall. It's just something like this on plan. That's the thickness. Right, so let's say this is my little a now, this is my little b now, and the thickness is, let's say, my little t. So what is so special about slab and wall or raft footing or raft foundation in terms of the dimension? So t, the thickness is usually very much smaller than a or b. So in this case, a or b is very much larger than t. Example, slab. A typical floor slab for a residential building, 150 millimeters. So t could be, let's say, 150 millimeters. That's very typical. And then what about the dimension of a slab? Let's say 3 meters, 4 meters. So A and B could be 3 to 4 meters. 20 times. It's much larger. Right? That's what we mean by much larger. For a raft footing, usually raft footing is much thicker. So for raft footing, let's say, for a raft, thickness could be a bit higher, let's say 500. But then the dimension is much larger on plan. Usually a raft would be quite big. So we're talking about 10 meters. So A and B in this case could be, let's say, 10 meters. Right? So you can see the difference between these various dimensions. Right? So if you keep extending the concept, 1D, 2D, and then you have 3-dimensional. So for 1-dimensional, you can see the length is larger than the other two. For 2-dimension, the on-plan size, A and B, is much larger than the 3rd-dimension thickness. So can you imagine what is the 3rd one? In the 3rd one, A, B, and T, the 3 dimensions, are very similar. There is no significant difference. So let's draw it first. If those 3 dimensions are more or less the same, what does it look like? It's like a cube. So it's something that looks like that. Just a big piece of material, concrete. So in this case, this is my A, this is my B, this is my little c, let's say. And we say, for this case, A, B, and C are of same order of magnitude. Right, that's the technical term. We don't say they are similar. They are of the same order of magnitude. And this thing is also very common in building structure, but usually you won't be able to see in the superstructure part. It's in the foundation. It's the pile cap. So a typical example is a pile cap. So what is a pile cap? A pile cap is exactly something like this. So it's a big piece of concrete. It's a large piece of concrete, usually very thick. How thick? Let's say at least 1.5 meters. It can go up to 3 meters. So it's a very thick piece of concrete, just 1 floor high. 成層樓咁高. It's a huge piece of concrete. It's very thick. But the plank dimension is also, right? So the plank dimension, it could be, let's say, 6 meters. 6 meters. This could be, let's say, 8 meters, something like this. Right? So you can say these 3 dimensions are of same order of magnitude. There's no big difference between them. 好似嚿大嘅磚頭麵包. Why you need such a huge, big piece of concrete? Because it's going to support a lot of load. Like most commonly, it's going to support the lift core, right? The core wall. So let's say you have 2 lift shafts. The lift core would look something like this, right? Something like this. You have 2 lift core, right? That is your core wall sitting on the top of your pile cap. What do we eat? Right? The lift core. And it's very heavy, supporting the whole building. It's very heavy, so that's why you got a big piece of concrete to support it. And beneath the cap, of course, you have piles. You have a number of piles underneath. This is a typical 3-dimensional element. And the good thing about these 3 classes is, for 1-dimensional and 2-dimensional, why we need to classify these elements? Because the principle for 1-dimensional elements actually equally apply to 2-dimensional. So if you understand the principle for 1-dimensional elements, you can apply the same concept to 2-dimensional. The only difference is an additional dimension, but the principle are exactly the same. So if you know how to do a beam, you know how to do a slab. If you know how to do a column, you know how to do a wall or a rafter. Same thing. But 3-dimensional pile cap, those things are different. This one is an exception, right? They have a different set of principles. So beam and slab, basically, I can draw a length between them. They're based on the same principle, very similar principles. Columns and walls. Okay. Right, so that is something about elements. Right, so here you can sometimes 1D element is also called 1-dimensional rod. Oh, by the way, 2-dimensional elements can also be, it doesn't have to be a flat plate, it can be a curved. 1-dimensional element, it can be a straight member or curved member. Same thing applies to 2-dimensional. 唔係一定一個平面嚟嘅 flat plate, a flat surface. It doesn't have to be a flat surface. It can be a curved surface. Right? Same as 1-dimensional. 唔一定要直，唔一定要平。It can be curved, 線或者曲面。And another new word, prismatic and non-prismatic. Beams doesn't have to be prismatic. That's also very common in building structure. What we mean by prismatic. Maybe I just put a little sketch at this corner. So usually a beam would look something like this. Assuming the cross section is rectangular, so it would look just something like this. So what that means is the cross section, the size, it's the same everywhere, right? No matter it's here, if you cut the section here, it's the same. If you look at it on the other side, it's the same. So the cross section size is the same everywhere. This is called prismatic. Prismatic. But very often in building structure, you can see everywhere. It's very common. You have non-prismatic beam. So what we mean by non-prismatic, that means the cross-section is not the same everywhere. It changes. So how does it look like? Well, one simple example is you have the same beam here, same cross-section, but then the cross-section get larger towards the other end. So I can draw something like this. So you can see on this side, the cross-section is just that much. It's just a small rectangle. But on the other side, if you look at it this way, it's much bigger. So the size is getting larger and larger from the left to the right. Or from the right to the left, doesn't matter. So this type of members is non-prismatic. To make it more complicated, you can also have a curved non-prismatic beam. Right? You can also sketch for yourself a curved and non-prismatic beam. Alright, so in the next few slides, I just try to cover a few examples, some real playing, 5 more slides before we take a break. Alright, we'll try to cover up to this picture. So in the following 5 pictures or slides, I just want to point out the importance of geometry in structures. Right, so on the first slide here, you have definitely seen this before in your contact course. This is called, to be more accurate, this one is not a flat slab. This one is a flat slab. This one actually is a flat plate. This one is a flat slab. Right, so on the left you can see this is just a typical reinforced concrete slab supported directly on columns without beams. So there is no beams, so without beams. Right, so what I'm going to assume is, let's say this is a slab for a not residential. Residential, usually the live flow is small, unless you have the machine room or some plant room. Otherwise, the loading is light. Let's assume this is an industrial building, right? So if this is an industrial building, the loading could be, the live load could be, let's say, 7.5 kPa. Are you familiar with this new unit? Okay, it can go up to 10 kPa for industrial. Right, industrial building. Let me give you some other numbers for comparison. For car park, right? For car park, what do you think for a car park? The live load is smaller or larger than this one? Any guess? For a car park, is it larger than 7.5 or 10? 7.5 up to 10 is for industrial building. For car park, the live load is larger or smaller? This is a good quiz question. A or B, larger or smaller or the same, or none of the above? Sorry? What situation? Of course, we are assuming all cars are there. We are not assuming an empty car park. Heavier. What about you? Yes. Heavier or lighter than this? Same. You? Heavier. How many say heavier? I mean, car park is heavier. It's lighter. Industrial buildings usually are much more heavy. The machines there are much heavier than cars. Cars are actually not that heavy nowadays because the materials are getting lighter and lighter. Right, so suppose, what are we going to talk about? Right, suppose there's heavy loading acting on it. And suppose, imagine that you have relatively small columns. So what I mean is, let's say these the cross section is just a square. So let's say these are 300 millimeter square. So 300 times 300, I mean, millimeter square. 300 by 300. Relatively small columns. Okay, it's not a big column. So what happens if you've got heavy loading on it and small column supporting that thing? What happens? That again, of course, is common sense. Oh, I don't want to. Right, so this is small column. Imagine this small column. This is the slab, very heavy loading. And this is supporting this heavy slab. What happened? Punching, yes. That is what's going to happen. It will punch through the slab. If that thing is supporting heavy slab, heavy loading, and this is a small column. So the next question is, how are you going to avoid this from happening? Proposal number 1, less loading. Loading? No. Why? The BD sets for industrial building, it has to be that number. You cannot change that number. So the loading has to be that heavy because it's an industrial building. There's no way you can change it. Second, option number 2. Can we make this slab thicker? Yes, that's possible. But if you make this thing thicker, that means you need to use more material. More material means more money. And it's more heavy. If the whole building is more heavy, that means you need a bigger foundation. So everything down to more money. That's a possible option, but not a good option. What about making this thing, instead of using this little column, can we make it a big column? that probably won't punch it through so easily. But if you make a bigger column, that will occupy more floor space, just like the big column behind you, right? If you got a big column, then you'll take more floor space. The client won't like it, right? So the better option is, if you look at the slide there, instead of making the whole slab thicker, why don't we just make the slab a little bit thicker around this area? So that's why you see on your slide, you have this drop panel. I don't want to make the whole slab thicker. I just need to make it thicker around the column. Why you need to make the whole thing thicker? It's no point. Wasting material, wasting money, wasting or proposing a bad solution to your client. And I want to make the column a little bit bigger. But why you need to make the whole column bigger? You only need to make the column head bigger. That's what we mean by a flat slab with a drop panel with a bigger column head. And that will solve the problem. Right? That will solve the problem. Using common sense. So that will avoid the problem of punching shear failure. That is the problem behind for that thing. 我支筆篤穿咗張紙。The technical term is punching shear failure. And to avoid this from happening, you change a flat plate to a flat slab with drop panel, with a little bigger column head. You change the geometry locally, not the overall, just locally around each column. You change the geometry. You don't change the material. You don't change the layout. You just change the geometry locally. Right, so I can mark it local change in geometry. That will solve the problem. All right, so the next slide is a very typical roof system for stadium, for swimming pool. It's a very typical thing. So what you have for a typical stadium roof structure is you have a big column connected to some kind of foundation, whatever that foundation is, usually some power foundation. And then you have a roof, usually a very long span roof. But if you are going to connect your column with a very long span roof, then you may need a very strong member, because this is a very long span member. So instead of using too much material here, instead we try to support this thing